right, so let me go here. All right, so we're gonna can everybody see that the PowerPoint on the screen?
Yes.
Cool. All right, so we already talked about mass spec, and the example that we did on yesterday, I keep saying yesterday, on Monday, was dealing with identifying fragments, and we had 5 compounds, excuse me, that we were dealing with. And we said that based on the spectrum and the peaks that were in the spectrum, that there was only one compound that spectrum could correspond to. And we said that it was ethanol, if I'm not mistaken. And we didn't talk about ethanol. Hold on one second. So I need to show you the actual fragmentation patterns. Let me pull up my iPad right quick. I need to turn on a modifier. Well, I'm going to come back to that so we can explain how this is, how it's ethanol, how it's not something else. Because we ruled out formic acid. I showed you all the fragmentation patterns for that. And then we also ruled out all of the other compounds with the exception of ethanol, which had a molecular weight of 46 grams per mole. So that was the parent compound. And so because of that, that's how we knew that was ethanol. All right, so I'm gonna come back to that once this MiFi hotspot fired up so I can share my iPad. But let's go to, we already talked about that. So I want to talk about these fragmentation patterns and how you can kind of predict where certain things are going to fragment and where they're going to break. And so when you have a molecule like the one up top, like a branched alkane, those are going to, and again, remember, what you're fragmenting is the radical cation. You're not fragmenting the actual neutral substance itself, but that substance after it has lost an electron, right? So you have this radical cation that you're subjecting to basically being pulverized by an electron beam. And when that happens, you lose one electron, you have this cation, and then it continues to get pulverized, and you basically beat it to the point where you break it up into fragments. So if it is a branched alkane like the one up top, the normal fragmentation pattern is to fragment or break at a branch point, like I have shown here. You see the little squiggly line breaking at that tertiary carbon. So, and then again, when the molecule gets branched or gets fragmented, one of your fragments is going to be the cation, and one of them is going to assume the role of the radical. So in this case, the cation is on the secondary carbon and the radical is on the primary carbon, because that primary radical is more stable than a primary carbocation, which we have really beat to death over this semester, just dealing with carbocation stability. If it's allylic, like the compound that's shown here, right? We also know that if it's allylic, that's a cleavage point, right? That's a point at that allylic carbon where you can have cleavage. And as shown in the example, you see that the carbon, the CH3 that's attached to the allylic site is now a fragment, right? And we'll make that the radical, and we make the allylic carbon, that's CH2, the carbocation, because again, the carbocation is more stable as allylic than it is as a methyl group. All right, and then when you look at these other functional groups down here, like alcohols and amines and carbonyls like ketones, you have what's called alpha cleavage. This is another term of description that we've talked about, alpha, right? It literally just simply means adjacent to that functional group. So the carbon that's adjacent to the functional group, which you can see to the left or to the right, there's a carbon on either side of that of that line that's supposed to be indicative of cleavage, right? So those carbons become your cleavage point. So let me switch right quick because I want to show you this, the first example, and need to switch over to a different device right quick. So while I'm doing that, are there any questions about what we just mentioned? So I can import this thing real quick and switch over. All right. No questions about anything. All right. So these cleavage points and these cleavage patterns are common. So when you have a molecule that you have to figure out like what the fragments are going to be, it kind of helps you to understand like where to break things up. Like if you'll notice, like with the alkene in example number 2, with that allylic system, you're not going to break the double bond in half, right? You're not going to break off the CH2 on the end of a double bond. That's not going to happen, right? So and the same thing with the carbonyl. You're not going to chop that carbonyl in half either. So it doesn't work like that. So as long as you know certain patterns, then you can come up with a way to fragment any molecule. All right. There's some other patterns. We're going to come back to that alpha cleavage in a second, but there's some other patterns also. And if you look at the like if you have an alcohol, one of the patterns for alcohols is dehydration. And one of the things that you look for in dehydration is one of the things you look for is that. Right. I think I'm good. We switched over. That was seamless. All right, let me share my screen on here so I can go back to those cleavage patterns. Hold on one second. Coming up. Yeah, I'm not muted. All right. Here we go. All right. So let's go to here. Scroll up. So right here on this example, you can see in here that the cleavage happens again at these sites right here. Right. So if we were, and this is not simultaneous, you remember you got Avogadro's number worth of molecules in this solution that you inject. Right. So you're doing this cleavage on a molecule at a time. It's not happening twice on the same molecule. So if we did this here, we'll call it 1. Right, that's going to give us 2 fragments. Excuse me, 2 fragments. One is going to be here, and then one is going to be here as a CH2, CH3. That's this piece right here. All right, and this is always a point of confusion, so I want to make it very plain. There is a hydrogen here at this site, so we're going to put that in. When you break that bond, that hydrogen is still there. All right, that's really important, because if you don't understand that part, when you start trying to calculate the masses of your fragments, which is the most important part of mass spec, your masses are going to be off. All right. So we got these two fragments. And then you'll also have another set of fragments if you cleave at position 2. Right. Well, you have a 3-carbon chain like so. And then you have that. Right, because you're actually breaking the bond between these 2 carbons right here. Let me switch pins. All right, you're breaking this bond. So when that bond breaks, those 2 pieces are now separate. All right. So if we try to figure out the masses of those fragments, all we will have to do is add up all the atoms, right? All the carbons, all the hydrogens. And so let's do that for the original. And then let's see what we end up with. All right, so let's take that original molecule and let's calculate the molecular weight. So we're gonna erase all of this. Well, actually, I won't erase it. I'll just change pins. All right, so you got 1, 2, 3, 4, 5, 6 carbons. And then you have an OH, so the OH is 17. 6 carbons, that's 72. Because each carbon is 12 grams per mole. And then you have on the end down here, CH3. So that's 3 hydrogens, 5, 7, 8, 10, and then 13. So plus 13. So what is that? 102? That's 85 and 17. So the total mass is 102 grams per mole. So for a sample like that, your parent peak is going to be at 102. All right. What would the M plus 1 peak be for that molecule?
I have a question. Dr. Russell, I have a question.
Go ahead.
When you were talking about how the hydrogen stays bonded to the OH group, why is that?
Because you're not breaking the CH bond, you're breaking the carbon-carbon bond.
Oh, okay.
Yeah, it's like this molecule, if you had a molecule like this, you're only breaking this bond. Well, hold up. I gotta do something a little bit different than that. So you'll only be breaking here, right? So those 2 carbons are what's being detached, but what's attached to those carbons stays put. So
Okay.
if you got 2 hydrogens here and 2 here, when you break that bond, those 2 hydrogens are still going to be intact. You're not breaking those bonds. You're only breaking the carbon-carbon bonds. If that makes sense.
It does. Thank you.
Mm-hmm. So let's see what we have over here. So we have, let's pick one and make it a cation. So we'll make this one the cation. And then we'll make that the radical. All right. And then so in doing that, now we need to figure out what the masses are. So this is CH2, CH3. So that's 14 and 15. So that's 29 grams per mole. To figure out the mass of the other side, we don't really have to add anything up. It's the difference between that 29 grams per mole and the 102 that we already calculated for the parent. Right. So what would that be? 73? So that's 73 grams per mole. And you do the same thing for the other side. This is a CH2 right here now. So that's 1, 2, 3 carbons. That's 36. And then 3, 5, 7 hydrogens. So this is 43 grams per mole. And then the other fragment would be 102 minus that, which would be, what is that? 59. 59 grams per mole. All right, any questions about that?
I have a question. I have a question.
Go ahead.
Yeah. Can you go back to wait? So the second fragment that you drew is when you cleavage the hydrocarbon on the left side.
On this one right here, or this one?
I can't see it.
Did my screen share?
It stopped.
Sure why. What about now? Can you see it now?
Mm-hmm.
So which one of the examples? The one on the left or right?
The right.
Right here.
Mm-hmm.
Go ahead. What's your question?
I was asking, did that come from? Would you please the bond on the left hand side?
Well, I have labeled as 2. Yeah, it's what I have labeled as 2.
Guess it was time to get in the game.
Because you're gonna, if you have 2 alpha positions, you're gonna get two fragments. All right. Did that answer your question, or do you still have a question?
I still have a question. You said what?
Okay, go ahead.
What was the M+1?
Yes, I was asking what would be the M+1 for the parent.
It'll be
If the parent, what would the M+1 peak be?
oh, would it be 70? No, 103.
Yes, and that's standard. Any molecule that you're analyzing, whatever the molecular weight is, the M+1 is that molecular weight plus 1. All right. Other questions? Any other questions? All right. Let's go to the next example, and we'll look at that real quick, and then we're gonna go back to this ethanol example that we were doing the other day and finish discussing that. So here you're gonna get a similar cleavage pattern, right? It's still alpha cleavage, still happening at the carbons that are adjacent to those functional groups that are present, be it alcohol, amine, ketone, doesn't matter. The same thing is going to happen. We have here you're going to get the same fragmentation pattern. All right, so I'm just going to change the functional group to NH2. And then this is CH2, CH3, and I'm going to keep this as the cation. Keep that as the radical, because one has to be one and one has to be the other. And same thing over here. And I'll make that the cation and make that the radical. All right, so this is, again, these are standard fragmentation patterns. So if you have a molecule and you're trying to figure out how it's going to fragment, you can apply these patterns. If it has an allylic site, and you know that it can undergo allylic cleavage. If it has a branch point, you know it can undergo cleavage at the branch point. If it's alkyl, if it has a functional group like an alcohol or an amine or a thiol or a ketone, then it can undergo alpha cleavage. And then also if it's an alcohol, I mentioned a second ago, it can also undergo dehydration. So let me go back to the ethanol example, and let's look at how we are able to assign that spectrum to ethanol. So on Monday, we talked about formic acid and how formic acid is, we could fragment it with alpha cleavage, but the fact that we didn't get a fragment that matched the base peak, which was 31, meant that we could not assign this spectrum to formic acid. So we said that we could assign it to ethanol. So let's see how we can fragment this, right? We can break it here. Right, and remember the molecular weight is 46 grams per mole. So we can break it there, and that'll give me two fragments that look like this, right? I'll have CH3, CH2 plus OH, and I'm going to make this a radical and make that the cation, even though it's primary, right? That's the OH will be bad as a cation by itself, so we don't want to do that. All right, so that's that. This is 29, and this is 17. So that totals up to 46. I could also break it here. Right, and this is where we'll see the base peak. Right, so that's going to give me a CH3. I'm going to make that as my radical, and then plus CH2OH that I'm going to make as the cation. All right, so CH3 and then CH2OH. This is 15 grams per mole. And then this is 31 grams per mole, which is the base peak. So that's basically all of our fragments from this spectrum. We got 46. We know that 45 is just the loss of a proton. 47 is M+1. The base peak, 31, we just showed how we could get that. And then the peak at 29 is that ethyl fragment. And 15 is methyl. So let me just write those in up here. So that's that. This is that. And then at 31, it is CH2OH. That's that fragment. And at 45, we can just say that. So the alcohol without the proton attached to it. And then 46 obviously is the parent. So that's going to be the molecule itself. As the radical cation. And 47 is the isotope peak. Right? So those are all the fragments that are possible for ethanol. Right? And remember, the reason why we didn't choose formic acid was because we could not get a fragment that matched the peak at 31. All right. Any questions about that or about anything we talked about to this point? All right. Let's go back to that PowerPoint. Oh, hold up. It's in the same app. And let's see if we can apply this, right? So here's and this is already broken up, but here's an example here where you have a reaction that happened between this alkene and MBS and light. What kind of reaction is that? Anybody remember?
Is it Harold bromination?
You're close. It is a type of bromination. It's a allylic bromination.
Okay.
Right? So with that allylic bromination reaction, we get this. So the thing is, how do you know you have that? Right? That's the question. So there are other methods that you can do. Obviously, you want to do NMR first, but you can also do mass spec and find this as well, right? So if you look at the molecule itself, right, this is a site for cleavage. This is a branch point. So this would be branched alkyl cleavage, right? It's also allylic. Sorry about that. Right, and then on the other side, this would be simply be allylic cleavage. Right, so if you look at the overall molecular weight of 190, whatever fragments you make from that molecule will have to add up to 190. So if I do look at the cleavage that's indicated by the red dashed line, that's going to give me these two compounds over here, or two molecules, fragments, and one of them is 42 grams per mole, and the other is 148 grams per mole. By the same token, on the other side, this is 111 and 79 because it has to add up to 190, right? So the bromine fragment is 79. That's the atomic mass of bromine, and then the other fragment is 111. So it's just a way to an example to see this. Now let's look at it in practice by looking at this example. All right. So the example says a patient mysteriously dies. It's believed that the patient has been poisoned by his wife, and the crime scene investigators suspect that the patient has been exposed to dioxin, which is the second deadliest poison on Earth, with a lethal dose of 5 milligrams per kilogram of body weight. How will they find out? So there's a couple of ways you can think about this, but one way to find that out is to do you can do a urine sample, you can do a blood sample. I mean, there are a lot of ways, but if you do a urine or blood sample, those are liquefied already. And so they're perfect specimens to do mass spec, because mass spec, you generally have to begin with a liquid, a solution, and you inject it into the instrument. So does anybody know what the deadliest poison on Earth is? Anybody? It's actually Botox. Botox is more even deadlier than dioxin. That's why it causes, and I always, every time I teach this, I always use that example, but that's why it causes the inflammatory response that it does, even at such low doses. That's why people inject it into their lips and cheeks and over their eyes and trying to, to get that full look, but it's actually a poison, and then it's eliciting an inflammatory response from the body. And that's why you get that fullness when you inject it into like a place on your body that may be wrinkled up or sagging or whatever. So, but with that said, this is dioxin. It has 210 different chemicals in this family. You can imagine they're all different isomers, where the chlorines are in different positions, or there may be 4 chlorines, or 3, or 2, or 1, or none, right? All those different constitutional isomers can exist. So this one that's shown is the most toxic. And this is a toxin, carcinogen, causes liver damage. It was actually used in the Vietnam War with Agent Orange. I don't know how many of you have ever heard of that, but it was a chemical weapon used by the United States in the Vietnam War. And yeah, nasty stuff. All right, so if we were looking for this in a mass spec, what parent peak would we look for?
324.
We'll be looking for this mass right here as the parent. So if they take this blood sample and they find a parent peak at 324, somebody's going to jail, right? So, and that's the goal, because if you're doing an investigation and you're doing some crime scene investigation and doing chemical analysis on things that are there, if this is what you suspect, that's one way to find out whether or not it's there. Now, don't get me wrong, you'll have to do more work, because there are, I mean, there are probably thousands of compounds that have a molecular weight of 324, but this one is going to have a specific pattern that is going to fragment in that you'll be able to detect by mass spec. So this is the mass spectrum of that compound. What do you think? I know the numbers are kind of weird, but that's only because I had to import this into this app. But if you look here, you see that the parent is indeed at 324. And then there's a peak at 325. What is that peak?
Which one?
The M+1. With this being a halogen, with there being halogens present, there'll probably be a peak at 326 as well, which would correspond to the M+2, which is only found when you have halogens present. All right, so you can see here, these are all the different fragments. And this is what I was saying, the fact that there are other compounds that might have the same molecular weight, but even if those compounds have the same molecular weight, they won't have this same fragmentation pattern. So you can see at 289, that's representative of this molecule here, with one of the chlorines being fragmented off. And then 254, that's another chlorine taken off. You can see these two chlorines here are now missing in this fragment. And then, as you can see, you can just keep going down the line and removing chlorines, and you get all these different fragments, right? And you can also cleave the bond, the oxygen aromatic bond between here, right? You can cleave that bond and get a fragment that looks like that. That's 177 grams per mole. So the bottom line is, this is a method used to confirm whether or not the presence of a compound is there. And based on his blood sample, his wife is indeed going to jail for murder, going to prison for murder, because when they took the blood sample, they found this dioxin fingerprint at 324, and all the subsequent cleavage patterns and all the subsequent fragments that go along with dioxin also matched up. All right, questions about that? Any questions? All right, let me need to pull up and introduce that, because that's our second method. All right, so we talked about this already. Infrared, we just introduced it, and we talked about it being another one of our methods for characterizing organic compounds. And the way infrared works is it allows you to identify certain functional groups that are present. Every functional group has its own signature absorbance in the infrared spectrum. All right, so this is I gave you a sample the other day, but this is a sample infrared. Everywhere you see a downward spike is indicative of and absorbance, or where infrared radiation gets absorbed. All right, so if it's flat, that means that there's no absorbance in that area. But if it's a downward spike, that means that infrared radiation has been absorbed there. All right, so with that being said, you have on the x-axis, that's the wavelength, right? But the wavelength is given in reciprocal centimeters, and the reason for that is because it's given as the speed of light divided by the frequency, right? So it's given in reciprocal centimeters. So when you think about infrared, what do we use it for? And I'll talk more about the wave numbers and all that as we go along. But when you think about this, it's really used for structure determination. If you make a compound, you need to be able to, and it has specific functional groups in it, like alcohols, excuse me, or amines, or alkenes, or alkynes, or any functional group that absorbs in the infrared region. Then an infrared you should be able to see those functional groups by infrared. So it's a tool for determining the functional groups present. And one of the things that we have to understand about infrared, how it works, the theory behind it, is the idea that two atoms bonded together are not static, right? They don't just sit. Like we might draw them on the paper with a straight line between them, but they're not just sitting there. Those atoms are in constant motion, vibrating back and forth, bending. The bond can bend, it can vibrate, it can wag, it can twist. There's a lot of different molecular motions that are happening. And those molecular motions are going to be intensified when the right infrared wavelength passes over that molecule. Because what you're doing in an infrared is you're actually bombarding your sample with infrared radiation at every possible wavelength in the infrared spectrum. So you bombard that sample with every wavelength, and the functional groups only respond to the wavelength that matches their current frequency. So if they're vibrating, I'm just using this as an example. If they're vibrating at, let's say, 5 reciprocal centimeters, then the wavelength that makes that excited is going to match. So when that infrared radiation of 5 reciprocal centimeters hits that bond, it's going to excite it, and then it's going to relax back down. But that excitation, you only need that once for it to be picked up by the infrared detector. All right. So this is an example here. Hopefully I can get it to work. So that's my bond vibrating, those two atoms kind of vibrating back and forth towards each other, oscillating. And then if I hit it with 100 nanometer light infrared radiation, nothing happens, right? If I hit it with 200 nanometer radiation, nothing happens. If I hit it with 300, nothing happens. And the reason is because the frequencies have to match. If the frequency or the wavelength, the frequency of the radiation doesn't match the frequency of the bond that's already vibrating, then it's not gonna do anything. But the minute I hit it with 400, you can see that the atoms become more excited, and so that excitation or that absorbance is what's picked up by the infrared detector, and then the infrared detector is you're able to get a number, right, based on the wavelength that hit it. All right, so only if the frequency of the radiation matches the stretching frequency, that's when you get a absorbance on the infrared spectrum. So if we go back to the first slide, all of those downward spikes means that whatever functional group is at, let's say 1600, where that little red tick mark is, after 1500, whatever functional group is there, it only got excited when it got hit by 1600 nanometer radiation, right? By the same token, if you look at the little tick mark after 1000, let me see, that's about 1150. That only got excited when that functional group got hit with radiation that matched that frequency of 1150 nanometers or reciprocal centimeters. All right. Right. So your wavelength for infrared is 400 to 4,000 reciprocal centimeters, which we call wave numbers. And we measure in reciprocal centimeters and not nanometers. But these are the wavelengths that we use for organic chemistry. We use reciprocal centimeters. And as the wave number becomes larger, because keep in mind that's the centimeters and nanometers, that's a wavelength, right? That's wavelength. That's not frequency. Frequency is different because the frequency is per second. Like it's a function of time. And the wavelength is a function of distance. So as the wave number gets bigger, the energy goes up. So stuff that absorbs way down 2,000, 3,000, 4,000 in that area, what that's indicative of is the fact that it takes more energy to get those functional groups to vibrate than it does something in the lower region. Because if you remember from CHEM, was it in part 1 or part 2, the energy of a photon is H times, which is Planck's constant, times the frequency of the light, right? That'll give you the energy. But that frequency can also be described as the speed of light divided by the wavelength. If you don't have a frequency, you can always derive it by using C over lambda. So that's why it's reciprocal in this case, because we're using C over the wavelength, and that wavelength being in the bottom on the denominator means that it's going to be reciprocal centimeters and not just centimeters or nanometers. All right, so you have these different intensities. You have weak, medium, strong, variable, and broad. So sometimes in the infrared spectrum, you'll see that. You'll see a W or a BR next to a signal or a value for a signal. And when you see that, those are your different intensities. So it could be a broad stretch, it could be a variable stretch, a weak stretch, so on and so forth. One of the things about infrared is that certain scenarios that are if certain scenarios in place, there's no absorption. So you won't see infrared absorption at all. We call it IR inactive. If there's no dipole, right? So if there's no change in dipole between the atoms that are bonded together, that's not going to be an infrared activity. You're not going to see anything. Also, if you have symmetry, certain types of symmetry, like what I have here, ethane, right? There's 2 methyl groups or 2 CH3 groups bonded together. If that's the case, then you're not going to see infrared activity, right? So if it's a non-polar or molecule that has no dipole, not non-polar, but no dipole whatsoever, then you're not going to see infrared activity. And if it's symmetrical, you won't see infrared activity. All right. So these are just some of the different molecular motions. So if I hit this molecule here, that with these 3 atoms bonded together, if I hit this with certain infrared radiation, right, I can get these different molecular motions. I can get stretching, where you can see how the arrows indicate that the central atom is getting pushed down while the 2 other atoms are getting pulled out. It can bend, where the 2 outside atoms are going downward, and which will in turn force the central atom to move upward. Kind of like if you were to bend a pencil, like if you take the 2 ends of a pencil and bend it, the middle part of the pencil is going to kind of bow upwardly. That's what it means when it says bending. And then twisting, there's also twisting that can happen where the 2 outside atoms just kind of rotate around the central atom. They don't actually come apart, but they rotate as far as they can. And it's these molecular motions that get intensified when there's a exposure to infrared radiation. All right. So let me go back to something I said earlier about wave numbers. And again, the higher the wave number, the more energy it takes to actually get that bond to do something, whether it's going to stretch, bend, wag, twist, whatever. The higher the wave number, the higher the energy, because the frequency is also going to be higher. All right. The wavelength is going to take it, the wavelength is going to be shorter, and that's going to cause the frequency to go up. And that means that the energy is going to be increased, because frequency and wavelength have a reciprocal relationship where the frequency is 1 over the wavelength. So the shorter the wavelength, the higher the frequency, the longer the wavelength, the shorter the frequency. So here, if you have a simple CH bond, right, that has a wave number somewhere about 2,800 to 3,000. You'll notice that with the wavelengths, with the wave numbers for alkyls, they always show up in the same place, somewhere in that range between 2,800 and 3,000. And then if you have a vinyl proton or vinyl hydrogen, that CH bond takes a little bit more energy to do that, to stretch it, because that sp2 carbon is a little more electronegative. So it's pulling the hydrogen closer to it, shortening that bond. So it's going to take more energy to stretch it. Triple bond, same thing. sp carbons, more electronegative than sp2 or sp3, shortening up that CH bond, making it more difficult to stretch it out. And so that's why you see 3,300 as the wave number for an alkyne CH bond. All right, we got to stop here. I'll pick this up on Friday, and we will finish this. We're gonna start NMR, and I'm thinking I have an NMR handout, but I'm thinking about switching and doing something different, just so that we can tie all this stuff in together and make it all make sense. But at any rate, we're going to finish this on Friday and start NMR. And I think that we can take another exam strictly over spectroscopy. It'll be more like a glorified quiz than an exam, but I think we could do that coming up. So I'll let you know when, and once we get through NMR, then we'll probably just take a quick exam over these topics. And then the final reactions, we'll just do those separately, and then we'll be done. We're actually in the home stretch, so that's a good thing. All right, any questions about anything? All right, if not, we'll log out, and I'll see you back on Friday, God willing.